Hello, everyone. Yeah, it's our pleasure to have Manuel here to share about his work on trainabilities, barriers, and opportunity in quantum generative modeling. Today, he'll be like sharing with us some new concepts, like that define some interesting concepts such as like explicit and implicit, like generative model and losses. And from this framework, you can see how mismatch of the explicit and the implicit losses will kind of harm trainabilities. And I think that Manuel will be able to like tell us more about this. And yeah, Manuel, okay. By the way, for the audience, if you have any questions, either you can raise your hand and then just unmute yourself to ask about question, or you can type it in the chat so that I could like help you ask the questions. And yeah, so Manuel, the floor is yours.
Thanks. No, this was a very good summary. I'm impressed. Yeah, so I'm Manuel. I actually only very briefly sat at the same table with Bengi because I was actually spending my summer in Los Alamos. But yeah, so this is one of our groups here at EPFL. It's actually our first actually group work that we also did a collaboration with some people from CERN. But this was for me, very satisfying and fulfilling work because it allowed me to, like me personally, to build a lot of the framework in discussion with my team members that then allowed us to really nicely frame the results that we then all produced so that everything kind of fell in place. And it's a very nice conceptual structure in my opinion. And so I will try to kind of show you around in this framework that we built. Okay, so quantum generative modeling is one of those, okay, so this is like a very overused slide, but okay. It's one of those kinds of variation quantum algorithms. You could argue that it's not a variational algorithm because it doesn't have the variational principle kind of as part of it baked in. But essentially, it's as any of these other applications of variation in quantum algorithms, there is loss function involved, right? There's loss function involved that you minimize according to whatever your problem is. And in generative modeling, that loss function is actually your comparison between a model and training data. But because it can be classified as variation in quantum algorithm, it suffers from the same kind of like enormous problem that is barren plateaus. And this is a little condescending to explain all over again to probably most of you, but essentially we would like our optimization landscape as we train our circuit parameters to look more like the left and less like the right, obviously, right? And so, but that's not just because we want to train quickly, right? So this is a common misconception. Small gradients or small variation between losses is not an issue of like speed, right? Of like moving slowly. It's an issue that you actually require high precision on your quantum computer to even distinguish losses and to even distinguish any direction, kind of like any gradient to any other gradient, right? And because you need high precision on a quantum computer, that means you need a large number of shots, right? So if you want some cost estimate to epsilon precision, you need 1/epsilon² many measurements from the quantum computer. And so barren plateaus are characterized by exponentially decaying gradient variances or gradient magnitudes as you add more and more qubits. And exponentially decaying means the number of measurements you need to actually do anything useful exponentially has to rise, right? This is the only way you can counteract kind of like smaller differences in losses with higher precision, right? And so you need exponentially many measurements, and that's obviously not going to work. And yes, so there's many reasons why you would have a barren plateau, and there's actually a couple, or like, yeah, there's actually a few nuances in generative modeling that make it very different to all the other kind of applications where you have the typical candidates such as expressivity. Okay, you also have expressivity in generative models. Noise, you also have noise induced BPs in generative models. Entanglement, you would also have that. And then global loss is where it starts getting a little nuanced, because the notion of a global loss, as in like a Pauli operator that acts on many qubits non-trivially, that's not really a thing if you're working with classical data. But okay, let's roll it back from what actually is generative modeling or generative machine learning, right? So there's this is kind of a slide that I made like 2 years ago plus. I should change it by now, because it's like this industrial kind of like sales slide where, oh, there's so much you can do with generative modeling, right? So this famous example, which now is like not even the most famous anymore, is like this person does not exist.com, where every time you refresh the page, a new automatically generated person comes up using a generative model. And so, but you could also think about molecular discovery, time series, anomaly detection. And the thing is always, you receive data, you receive examples. So if, for example, you receive images on the left, or you receive some normal and anomalous data on the right? So, and then from that, the model is supposed to pick up on patterns. It's supposed to kind of give good predictions, or in this case, in generative model, it's actually not predictions, it's like to generate data which looks like the training data, right? So with a similar distribution of like anomalous to unanomalous data, or with this is actually like a bias that also like generative models have for image generation. It tends to produce the skin color of the people who's kind of training, like who are in the training data. And so oftentimes there's like much more training data on like Western kind of looking people, which, yeah, so there is this bias that the model picks up because it tries to produce data that's close to the training data, but actually the idea is that it learns the patterns underneath it, is able to create new data, right? And so I guess NLP applications, now with like ChatGPT, that's like the newest application of generative modeling that actually works very well. Yeah, so it's the same, right? So you give it a lot of examples of text, it picks up on the patterns, and then you can actually communicate with it. So, okay, so what is the quantum version of this? So the prototypical quantum generative model is a quantum circuit Born machine, where the data now is not images, it's not like continuous kind of valued sensor data. For Born machines, it's actually just bit strings, like discrete data that you can kind of build out of bit strings. And so what is the model then? The model is a parameterized quantum circuit. I'm just like demonstrating this with layers, and the layers are made up of like further gates, and they're parameterized. And so you prepare the state with your parameterized circuit, and then you just measure. You keep preparing and measuring, preparing and measuring, preparing and measuring. And what we know is that the probability of measuring any bit string, the probability of measuring any like x1, x2 to xn, right? So like 0, 1, 1, 0, 0. The probability of doing that is exactly given here by the absolute square of this amplitude of the corresponding kind of like amplitude in the quantum state. So, and why is it the Born machine? Because this is the Born rule of quantum mechanics, right? That the probability of measuring something is given by the amplitude squared, like absolute square of the corresponding wave function amplitude, right? And so what the goal now is that you get a training set that, for example, that's like a distribution over all the bit strings, right? So these have basically 0 probability, and these have like high probability. And you're trying to learn a model that generates similar data. Okay, this doesn't look great, does it? But it's actually a trained QCVM. It just isn't powerful enough. It just isn't expressive enough, right? So it's actually with just one layer of whatever ansatz I didn't tell you. However, we can add a second layer, right? And so you can see that by making the circuit deeper, you gain more more flexible control over independent amplitudes, right? So you can push up amplitudes without probabilities, without getting like product state artifacts, kind of, I call this like here, right? So for example, without a CNOT gate, without any entangling gate, you couldn't create the distribution 0, 0 and 1, 1, like 50, 50. You would always get the product state artifacts like 0, 1 and 1, 0 kind of mixed in there. You couldn't get rid of them. You don't have this kind of like flexible control over which you push up and which you push down. And entangling gates, like right, the deeper circuits enable that. They give you independent control and the ability to learn, in principle, arbitrary distributions, or to represent arbitrary distributions, let's say. And why is this a model that we're even considering? Why is quantum generative modeling a thing? Well, okay, so the kind of like argument that we would like to say is something, oh, we can maybe quantum computers, because they actually are based off of these maybe you can pick up on more interesting patterns that classical models couldn't pick up on, and so you can maybe learn a better model. Okay, maybe, right? Maybe. What I think the biggest advantage is of quantum generative models is actually that they have a perfect sampling algorithm or a perfect sampling approach for the model. So oftentimes fitting functions is not that difficult classically, but actually sampling from them is very hard. And so quantum generative models are essentially the prototypical example of what a quantum computer should be able to do very well. Prepare a complicated state and create a snapshot, a measurement from it. Usually that's kind of like this collapse of the wave function is usually seen as kind of a detriment, like it destroys information. Here it's actually a resource, right? So we want one random example of the distribution of examples, right? And so it's actually exactly what we want from our generative model in general. We want to create one sample, one snapshot with exactly the encoded probability. There's no kind of like time bias, like that consecutive samples are somehow correlated, like in some Markov chain Monte Carlo algorithms. There's no distinction between, oh, this distribution is easy to sample and this distribution is hard to sample. No, the quantum computer does not care about these things. And so I think this is the biggest hope with quantum computers and generative models.
Sorry, I kind of agree with this, but then do you know how to calculate the cost of sampling? Because like for Monte Carlo sampling, then basically you need n square x polynomial is like quadratic to sample, and then it's basically calculated as a rate of convergence, right? How about like QCVM, like for like using quantum computer as a sampler? Do you know a way to properly calculate the cost in terms of time, for example? So like narrowly speaking, we just like use the time to run the single qubit and two qubit gates and the whole circuit to calculate time. Would it be too long?
So I'm sure there's a lot of literature kind of comparing different sampling methods on the classical realm. I don't know if they're, which I don't know how exactly. I mean, yeah. So convergence time, kind of like thermalization time, is one of those things. Like time to uncorrelated sample. These are things that people are looking at. Here, every sample also costs more energy in a way, right? But it's probably there are distributions which are interesting to us that are just so more efficiently sampled with a quantum computer that there's like no question that it's better. But otherwise, I think it would just be like wall time times cost times whatever. This is a very complicated comparison that I don't think anyone in the field really wants to do. I actually don't understand why. I feel like much more than thinking about, oh, how many more complicated distributions can a quantum generative model learn, I think the much earlier question is how much better is the sampling? And if we can't answer this, like don't even try with other stuff, right? I think it's so much at this point in time, after like works of last years, we know that sampling is definitely the thing that quantum computers have going for them. Learning and like learning is not necessarily their strength. So
Right.
yeah, I think there should be more focused on like actually studying potential benefits in sampling. One thing I want to like quickly say before we move on is that here it looks like so here this is like a 5-qubit example, so, which means there's only 32 bit strings. And this is not a real error probability. Usually what would happen is that you get a training set of bit strings and they are probably unique, and they're just like, I don't know, like 1,000 or 10,000 or 100,000 bit strings out of all possible bit strings, right? So right now this looks like super continuous, and every kind of like bit string has a probability, but usually would be like kind of like single peaks here and there in the middle of nowhere. Like this is how it would be as you scale up actually with more qubits. Okay, so there is a concept in classical machine learning that actually I don't think it's explored fully, but it's definitely out there, which is the distinction between explicit generative models and implicit generative models. This is right. So this has nothing to do with quantum yet. Actually, the quantum models just fit in this framework quite nicely. But this is totally valid for classical models as well. So explicit models are those that you can give a bit string X and they tell you the probability, like their own model probability for that X with a polynomial time algorithm. Right? So that's basically it, like to some like very high accuracy. Right? So whatever the accuracy is, you can always find a polynomial time algorithm for it. Usually this comes in the form that there is like an analytical form of your model where you can just like plug in X on one end, and it calculates and it gives you the probability. But also something like matrix product states actually have this. But okay, so implicit models are those that can't give you this probability in polynomial time to any precision. You only have access to the samples, and that sounds bad, but like in the end, samples are what you care about in generative models, and implicit models tend to be better at sampling. So, right, you will see that this is like give and take, but definitely explicit models have an advantage in training. Spoiler alert. So explicit models include autoregressive models, right? So you can really calculate exact probabilities, and also tensor networks. So for example, if you want the probability of or if you want to extract the amplitude of an MPS for a certain kind of like basis state, like a certain bit string, you just contract the one dimension, like one essentially representation of that bit string with the MPS, and you get a number, and that number is the amplitude. So you take a square of that, and you have your probability, right? So it's definitely polynomial time, because otherwise the MPS wouldn't, like you couldn't handle the MPS if it wasn't a polynomial time. Okay, implicit models are generative adversarial networks, diffusion models, all very successful, right? It just means there is ways to make it work. And also every quantum algorithm is an implicit model, I'm sorry. Why? Because, well, what are you going to calculate your probabilities with? You only have samples, like right? You can't do anything without samples. And we already discussed earlier when it was about BPs, if you want something to precision epsilon, and epsilon needs to be exponentially small, then we need exponentially many samples. And you can definitely imagine that if I give you an X and your model has this low probability, like an exponentially low probability on that, it takes exponential time. For other bit strings where it has like a big amplitude, okay, you can estimate that in polynomial time technically, sure. But you can definitely find pretty much always, just because if the wave function is normalized, you can probably always find, I think you can always find a bit string propose it, ask, okay, what's the probability? And it's exponential time to figure it out or distinguish it from zero, right? Like that's the thing. Okay. And what we actually developed in this paper is the categories of explicit losses and implicit losses, which exactly mirror the capabilities of explicit models and implicit models. So this kind of already suggests that there is some good pairing between them. And essentially, yeah, what we're going to show is that if you have an implicit model going up to an explicit loss, doesn't work. Okay. So to our results. So our first results, we have a lot of results then. If we have an explicit model that is like that has this form, right? So we sum over all the bit strings, and then we take some function of the probability of in the training distribution and the probability in our model, like our parameterized model. So what happens then? Common examples are, like the most common example actually is the KL divergence, but also like the Jensen-Shannon divergence, which people for some reason seem to prefer just because it avoids the log of zero, like log of potentially zero. But we show that it actually makes no difference training-wise. They all fall into this exactly same category of, here in this case, we call them pairwise explicit, because you always get kind of the probabilities in pair on the same bit string. And we show that because we have a polynomial number of training points in an exponentially big kind of bit string space, the probability that any of your generated samples and the model samples, generated samples and your training samples actually coincide, that probability vanishes exponentially with the number of qubits. And if you look at this, that just means we're going to get either f of 0 and something that we measured, or f of, okay, whatever the probability in the training set is, and 0, right? So there is literally no overlap between the distribution we sample and the distribution of the training set, right? And so this actually has so this is the problem, right? Without very good initialization, that would help, or strong inductive bias, so that your ansatz is already kind of tailored, kind of like focusing in on the training distribution. It's exponentially unlikely that we ever measure something that would actually give us a loss that isn't just some constant value. Right, and so this actually means that we need exponentially many measurements for different numbers of qubits here, exponentially many measurements to actually get away from this kind of like fixed point value that we get by replacing always one of these two here with 0. That's a constant value. And we need exponentially many samples with 30 qubits, right? Even until like 1 million samples, we're still at this constant value. We still haven't clicked and actually measured the same sample that occurred in the training set, because it's just poly-target at exponential space bad, right? So yeah, we show that you can't pair naive implicit models, and in particular quantum generative models, with these kind of losses, if you don't have a very good initialization or like some strong inductive bias. So explicit losses are not trainable with these kind of naive generic models. But like naive generic models is essentially what you always assume for BP results, for barren plateau results. Like if you don't know any better, random ansatz, random initial guess doesn't work, or doesn't scale at least.
So for the inductive bias that you say here is kind of the similar inductive bias that mentioned in supervised machine learning literature. Is it the same, or is there any extra bit that's specific to generative modeling?
It's an inductive. Okay, I actually don't know how it's used outside of generative modeling. But inside generative modeling, this is the same inductive bias that I'm referring to here as what machine learning engineers use in the classical literature, which is that there is your model, it's kind of like limited expressivity, but where you need it, right? So it's like it's a model that's tailored so that it can that it's particularly good at exploring the space where the solution is likely to be, and it's probably worse than a naive model at exploring everything else. Right, so it's kind of like this targeted expressivity kind of thing.
Yeah, but as in like based on your kind of like experience, is it for real world data, is this kind of like restricted space easier to find for generative modeling, or is it like hard to find in general?
So convolutional neural networks
Mm-hmm.
are an example of a model with inductive bias to locally correlated pixels.
Mm-hmm.
Right, so convolutional networks are actually a subset of all-to-all layers, but they work much better at learning images,
right,
or learning from images, because they assume that the most important knowledge is close by, which it is in images, right? Okay, and then long-range knowledge does matter, long-range correlation. So like that's why they mix into smaller and smaller layers, and then eventually kind of inflate information from global like starts to overlap locally. But convolutional networks are a perfect example of inductive bias for something like images. Yeah,
okay.
So it's very important. Like it's very important.
Yeah, this one is a good example.
Yeah. With transformers, it's funny because transformers have this like window of attention, and they just compare all to all inside that. I don't know what the most modern way is of doing this, but it seems like there should be some inductive bias there as well, where at least it looks inside a sentence, or like, I don't know, like all to all is always something that will just eventually not work.
Yeah, okay.
Right, so, okay. But this is an example of inductive bias, and we have no good idea of doing of how to do inductive bias in quantum machine learning models in general, or like quantum generative models especially for classical data. So there's obviously something you can do. I'm also working on a project like that, but you definitely need it. Otherwise, no go.
Right, okay.
Okay, what happens with implicit losses, right? So this, I suggestively already put them on the same level. That implicit model, implicit loss, there should be something there. What is an implicit loss? It's a loss that takes samples from your model, because that's the only thing it can give you, and the samples from the training set. And then it takes like some sort of like distance between this, and you take some expectation. And so this is what an implicit loss is. One example, and there's actually not many, not gonna lie. So generative adversarial networks by construction actually have an implicit kind of like learning like loss function essentially. So they are also an example. But for something like QCVM, which doesn't have an adversary, one of the few practical implicit losses that there are is the maximum mean discrepancy, or MMD loss. What is it? So it's essentially you pick a kernel, and then you just throw in samples from your model and samples from the training set, and you're essentially comparing the kernel statistics, like how often do you get a big kernel value and a small kernel value, throwing in either samples from just the model, samples from model and training set, or samples from just the training set. So the statistics would kind of be the same. This is why you have like positive sign here, minus sign here, and actually times 2, right? So the minimum of this is 0, and it's 0 when essentially the statistics inside the training set are the same statistics as inside your model, and like in the terms of generated samples. And one of the important factors here is that we have this kernel that takes like x minus y, and we chose the 2 norm, which actually turns this very discrete, okay, like yes or no kind of question, like does it overlap, does it not overlap, to like a continuous thing, right? It smooths out the orthogonal bit strings inside this kernel space to actually have non-zero overlap, technically with every bit string, but we can choose this like this bandwidth parameter of this Gaussian kernel so that it overlaps more with closer bit strings, right, and less with other bit strings that actually are basically not at all with like bit strings that are completely flipped, right? Okay, so because like Gaussian you have like exponential square decay, so in terms of distance. Okay, but this already gives you the sense that the bandwidth of this Gaussian kernel kind of needs to determine trainability, because if we take it to 0, we get back an explicit loss, and that doesn't work. If we take it to infinity, there's no distinguishing factors between any bit strings. They all appear the same. So obviously there's somewhere where it's optimal. And so yeah, we actually like worked on that, and we actually basically found it. But the way we did this is actually by taking this loss estimate as taking the expectation of an observable. So if we write an observable, this MMD observable, which is diagonal, kind of like this acts on this kind of two registers of X bit string and the Y bit strings. And on this diagonal, it has the corresponding kernel values entries. You can see that if you give it the samples as X and Y as like, right, so you take the expectation with X and Y from both sides, it actually picks out the only one where it's not orthogonal, like, right, so where X and X prime is like delta X, X prime, and delta Y, Y prime, and it picks out the correct kernel value. So you can see this also as the eigenvalues of this diagonal operator. And then, right, and so then the actual loss estimate is like trace, it's like trace of this observable with these effective, okay, so now you have to substitute either here 2 times like model, and then like some effective, fully mixed kind of like data state, or just like this kind of data states. It doesn't really matter in this case, but we can look actually at this MMD observable and work with it directly, because we know from VQA literature, if an observable that we're trying to like estimate the expectation value of is global, we run into BPs, and if it's local, we actually have trainability guarantees. Okay, so another way of writing this observable, if we now actually assume exactly this kernel, is as this. Okay, Sasha, was this Bernoulli or no? It was binomial, right? So we figured out that we have essentially have it wrong in the paper. It's a binomial with a binomial coefficient, not the Bernoulli kind of distribution. Wait, I'm still not sure, but okay. Okay, never mind. So we have binomial. We have here the binomial coefficient, and then we have this combinatorial, essentially, amplitude per diagonal operator. So what is this D to L? That's a diagonal operator that consists of identities and Z Paulis. So we transfer this actually into Pauli basis. And so if it's D2L, or actually just D2, it's 2 local. Whereas if it's D4, it's 4 local. If it's D8, it's 8 local. If it's D1000, it's 1000 local. Right, so we can see that this goes from essentially being 0 local to being 2n local. And each of these kind of like so-and-so local or so-and-so global terms has this amplitude with a probability, effective probability P, which is given by our kernel value. I'm not giving you the formula here, but it's given by the kernel value. And so how does this look? So if we say, so right, so this is kind of this is essentially the amplitude of, like, this is this amplitude here plotted kind of per 2L, right? Like, so the Spotiness K is essentially the 2L here. And so for 200 qubits, so this is all analytical this way, where you can plot this even for 200 qubits. If we choose sigma equals 0, which is the explicit loss case, we get kind of this distribution here, right? So this is kind of this binomial distribution on, like, centered around 100, around like n half. So this is kind of maximally global in that sense. There's basically 0 contribution of order 1 local terms and only contribution of order n local terms, which we call global terms, right? Order n is global. And so if you keep increasing this, if you keep increasing your sigma to like 1, or to n over 4, it actually makes it like pushes the bodiness, like the amplitude, large amplitudes to the left, it pushes it to local operators. And actually for n over 4, this is actually n over 4 is approximately optimal for product states, like for training product states, but essentially n over 4 is good enough for the to see it as the optimal bandwidth in terms of maximizing your trainability. And what that means is it actually maximizes it always has a large amplitude on these order 1 body terms. And so what that means is what people usually do is like they pick pick sigma 1, 2, 4, 8, and they average over it, which gives you kind of the surface. So the screen surface here is kind of the average if you average over these 3 kernels. So you see it's not normalized, right? So really, so you actually gain the best of all worlds if you wanted to by like averaging over several kernels. But actually we find that if they're all order 1, you still have exponential, you're still going to have exponential decay in your gradients and loss variances. But if you choose it like roughly n over 4, you actually have the largest loss variance which you can have. And this is not just hypothetical. So we did this for product states where I said we had like an exact solution for it. And we actually see kind of the theory lines in terms of like how the variance of the MMD decays would actually perfectly fits our kind of like finite shot results that we get. So this was very satisfying to like see for the first time, as you can maybe imagine.
Yeah, this is very cool. Numerical simulations like match exactly about theoretical predictions.
Yeah, made us very happy. But like the point is, if we have like sigma equals 1, exponential decay, sigma equals 10, it's fine until it isn't, right? Because the point is we need sigma to scale with the number of qubits to actually maximize our variance. And so this is actually training, right? So this is 1,000 qubit training or up into 1,000 qubit training. It's just product states, right? To learn a single like just the all 0-bit string. But even if it's just all 0-bit string, if we choose sigma equals 1, we just always get stuck here. We never move. Even for 100 qubits, but for 1,000 totally. But even for 1,000 qubits, you can still actually train and actually learn a bit string. That's crazy, right? Mm-hmm. And for deeper circuits, right, because this was product states, for deeper circuits, we actually show that if we have an n over 4 as our bandwidth in this kernel value, we have even up to 20 qubits with a bunch of layers. We have non-exponentially vanishing loss variances on like some random and some kind of like synthetic kind of data set with structure. So that's good, right? This looks like just use a big sigma, like roughly n over 4. If you choose a bigger, you get into this regime where every bit string is the same and actually like kills trainability again. But yeah, so this looks like n over 4 and you're good. No, it's actually, so it looks trainable. It is trainable, technically trainable. But what it doesn't reveal is that a loss with only n over 4 as your sigma, or in general, if you have any observable that represents your implicit loss and it's only local, it's actually not like you can't learn complicated distributions. Technically, that means it's not faithful. So if you have an MMD operator, or actually any operator, we show that this is for any generative modeling loss operator that you can write like this in a diagonal form. If it's up to k local, and it has like negligible amplitudes for more global terms, it can learn distributions. It can learn distributions that match the target distribution up to the k-body marginals, like the k-body I will show you, like, but not beyond, which means that there's just an infinite amount of distributions that have the same loss, which is zero, the same zero loss, but that actually don't match the target distribution. They only match the lower body marginals. So if your distribution is highly correlated, which means you actually need to keep track of very high order marginals, you can't use a local operator. It's just wrong. Like, it's just wrong to use an MMD with sigma equals n over 4. And just to show you what marginals are, let's consider this uniform distribution over 3-bit strings. And this one, where the third bit is always the kind of bitwise addition of the first two, right? So 0 plus 0 is 0. The other is obvious, and then 1 plus 1 is 0 again, right? So it wraps around. Okay, so what actually happens if you just look at two subsets of 2 bits at the same time, they actually look exactly the same, right? This is what it means learning up to some marginal. So if this is your training data, but your loss function only contains up to 2 body terms, so you made it like very local, great, now it's trainable, but it actually leads you to the wrong distribution. Or like you can't control to which of the distribution in this, like to which of the infinite distribution it belongs, it will kind of guide you that all have the same low body marginals. And so, yeah, it might be trainable for generic circuits if you make it local through this maybe optimal sigma that we have derived, but actually has limited learnability. Like you can't control what it learns at like high order correlations. And yeah, so that's kind of bad. But we have realized that you can average over kernels, right? So you can have low body terms that make stuff trainable. You can have kind of medium body and kind of like actually global terms. And the fact is, you need all of them at some stage of the training. So this is what we're showing, right? So you definitely need, if you don't know what you're doing, you have no very strong inductive bias, nothing, you definitely need local terms to start training, but you definitely need global terms to learn global correlations. So I don't know what, like each loss has to deal with this like its own way. For the MMD, you can average over kernels. Still, you're not necessarily guaranteed to actually converge to the globally correct solution. For stuff like quantum GANs, you can imagine that you want to initialize your discriminator so that it effectively is like a local operator, like a local observable, but then as it trains, needs to shift to a more global eigenvalue structure, because otherwise it can't learn the target distribution. It also means that if the target distribution requires this, has very high order correlations, that the discriminator actually needs to be able to capture that, which, yeah, so it's a lot of moving pieces, but we show you need both. You need trainable and you need faithful, which means global, like losses. Yeah, okay. So, and finally, we actually just did a kind of 180 and made a quantum strategy, which is basically exactly VQA type. And that is the quantum fidelity loss. So what we now do is we encode our data distribution into a wave function, where actually we also propose a way to do the training without ever loading this into one function, just by doing Hadamard tests. So you load it to a wave function, you have your you would usually have kind of a global zero projector here to measure the fidelity, but because that's global observable, there is actually a local version that's provably faithful, right? So it only consists of sums of single qubit projectors. That is local and that is faithful, and right. So if you use a quantum loss that shows it can be both trainable and faithful at the same time, which it can't really if you use a classical loss. And then we take just like 1 minus this fidelity, and we show, okay, if it was global, so if we'd had like the global zero projector, it would just decay exponentially with the number of qubits. But since we're using the local fidelity, it actually has polynomial decay up to 20 qubits with a bunch of layers. So this is looking good. Yeah, so we tried this. What does it say up there? Can be both trainable and faithful, exactly. Okay, perfect. So we actually benchmarked this on some data set, which is like Monte Carlo simulations of some CERN experiments and down sampled to 16 qubits. And we, so it's like, did like a bunch of repetitions, also scaled up to 16 qubits, but I'm not showing these results. And always with actual finite number of shots, MMD is essentially the best. And the KLD, the more qubits you add, just completely like falls flat. You can see kind of the target values where these black lines, and the KLD is just random, like it just does like nothing. Whereas the fidelity and MMD clearly have learned something. Now, why this gap exists between MMD and local quantum fidelity is not quite clear. I have this personal belief that local quantum fidelity is not going to be practical because you're essentially forcing a certain phase pattern onto your data, right? So if you go back to this, formula here, right? So you're forcing positive and real amplitudes, whereas if you did it with a classical loss, the phases would just not matter. So there's like many more solutions that satisfy the same optimal distribution. Whereas if it's fidelity, actually you're forcing a state, right, which has like a very specific, so your ansatz needs to be particularly tailored to produce these real positive phases. Plus there's the thing that, okay, so there's some other thoughts I have on as to why fidelity might just be worse than classical losses for classical data, but this is mostly speculation. Key takeaway is that quantum strategies, if you have a quantum loss, but even if you have classical data, they can be trainable and faithful at the same time. Whereas classical explicit losses just don't work, and classical implicit losses cannot be. I mean, you have to do something to make it technically trainable and faithful at the same time. Either like averaging or some weird protocol to like adapt bandwidth. That's weird, right? And for quantum strategies, we just need more of them. Currently, we just have the local quantum fidelity, and we need more people to work on this and propose new ones. So to give you a short rundown, explicit losses, no. Implicit losses can be trainable. You always have expressivity VPs, which means if you just make your circuit too deep, too expressive, or too entangling, it's not going to work. The problem with implicit losses is then that they can be trainable, sure, but also they can be unfaithful if you make them just local. Quantum strategies, yeah, I mean, please do work on this if you're interested. They certainly can be trainable and faithful at the same time. So yeah, we in other avenues that kind of go beyond just naive models is like what actually happens with inductive bias, what actually happens with a good initialization. And so numerically, this is easier to test than analytically. We're certainly trying. And then what happens with generalization? Because the end-all goal, I guess I haven't focused on this too much, because if you can't train, you can't use generative models. But the end-all goal of generative models is not to perfectly memorize the training data, but actually to learn the patterns of the training data and generate new stuff, right? And so kind of like how good your generated stuff is based on how well you learned. This is called generalization. It's called generalization or generalization error, depending on how you measure it. And this is the actual goal of generative models. And I haven't touched on this so far at all. But yeah, so this is kind of the next step that comes after being able to train. It's like, how well does it generalize? And yeah, we're also working on that. But yeah, with that, I'm basically done. I love this picture up here. I think it's so fun. I think it resembles our group very well, but now we've actually gained more members, so I should soon update this once we have pictures. So yeah, watch out for our growing group. And yeah, thanks.
Yeah, cool. Thanks, Manuel, for the very interesting talk, as in like your work basically kind of like give a lot of red flag what cannot be used. And I think that your work is kind of the first work that do proper theoretical analysis on generative modeling for quantum. I think.
Yeah, there's a couple people that did like things here and there, but essentially this is the first work that actually puts a lot of vigorosity to the field. Yeah.
Mhm.
Yeah.
Yeah. For the audience, if you have any questions, then you can unmute yourself, ask, or type in the chat. While they are thinking, maybe I can ask a couple of questions. So, you mentioned that like the Q GANs is an implicit loss, right? Do you kind of like keep a definition of why it is so?
Yeah. Okay. So why are Q-GANs implicit losses?
Yeah, implicit. Yeah.
So let's look at this here, right? So we have a diagonal operator, and there's this value here that for the MMD is given by the kernel. But that's okay. What would the GAN kind of the Q-GAN equivalent look like? We're putting in a sample X, and we're getting an output of the discriminator, right? So it would be just one register, like throw away the Y. It would just be the X projector, and then the eigenvalue would be the outcome of the discriminator. And that would be the GAN observable.
Right.
And then the actual kind of like loss function would be the average kind of like the average prediction of your discriminator, essentially. So you can put this into a logarithm. Then I guess you would have log of the prediction here and would average the log, right? Sure, that also works. But essentially it's prediction of the operator for sample X times the X projector. Like this is how the observable then looks like. And we show that this non-faithfulness for like low body observables, this holds for any loss that you can write as the expectation of such an observable. So like GANs have exactly the same problem.
Right. So even those like GAN,
quantum
you
GANs.
Quantum GANs, you can potentially train it, but then it's not faithful, and then you can only learn like low bodies, observables, and the distribution and the body marginal distribution problem that you have mentioned.
Right. It means at the beginning, maybe this kind of effective observable which is given by the discriminator, right? So the initialization of the discriminator needs to be such that it looks more like this kind of like golden at the left. But then as you train, if the data set requires it, it might have to like move to the right. Right. But it needs to happen obviously slow enough so that the generator that kind of tries to catch the gradients is never so far behind that it kind of it's too global for its kind of closeness and can't learn anything. So it needs to be this kind of in tandem training. Right. At least this is how we imagine it. Maybe but actually in practice will turn out differently. But yeah.
I see. And we didn't really know what is the like kernel bandwidth equivalence parameters in QGANs, right? I think currently it's still an open question, so how do we control?
Oh yeah, so it's right. So it's the equivalent would be the architecture of the classical of the discriminator if it's classical or quantum, plus its initialization, right? So if it's a quantum discriminator, it's actually very clear that you want to avoid deep random initial guesses. If it's a classical discriminator, like actually a neural network with non-linearities and all this kind of stuff, it's not obvious at all what it would take architecturally to create a local kind of QGAN observable. Yeah, I don't know these things.
Right. So it's some interesting question to ask. Okay, there's currently no question from the audience for the moment. So maybe I could like ask another one. So I think in your paper you mentioned that there might be one way to use the explicit losses is to compute
Sorry, can you repeat the question?
no, as in yeah, no worries. So in your paper, basically you mentioned that, okay, there could be potentially one way of using like explicit losses, but we have to compute, for example, the loss functions using our quantum computers, right? Or
Yeah,
maybe
that would
if,
go, that would, right, that would be a quantum strategy, we would call that. Like if you find a way to calculate a log of something like directly on a quantum computer, where the like epsilon error isn't on the probability, but actually on the log of the probability, right? Stuff like that. If you could do that, that would be an a quantum strategy for an explicit loss, just like the quantum local fidelity is a quantum strategy for the classical fidelity loss, which is actually explicit as well. But like logarithms, we don't think you can, in general, calculate on a quantum computer, especially the logarithms of probabilities. It's just like a thought experiment, but there's very certainly things that you could do on a quantum computer that would make some explicit losses trainable.
Right. Yeah, I think it seems like there's no question from the audience. Maybe they just like need some time to digest and think about all the kind of
Yeah, it's a lot of
details
stuff.
that you have, and then maybe because like your stuff is definitely new. Yeah, even to me they are kind of like implicit, explicit. I kind of like keep kind of like not sure like which one is which. Like for explicitly explicit loss is like it's based on, for implicit law will be based on sample, and the explicit law will be based on like probabilities. Yeah, I take quite some time to kind of like get that right. But yeah, as in like there are nice things about your papers, and then I think I definitely have to go read it properly and then ask some nice questions. I think it's like for the audience, maybe they could like send you an emails afterwards if they have any questions.
Yeah, obviously, feel free to reach out. I'm not running away. My email address, the one that you probably want to reach me at, is manuel.rudolph@epfl.ch.
Okay.
I think you might be able to see me as like a CC in your invitation emails.
Oh, right. Yeah, that's right. Yeah, I kind of see you in the image.
Yeah.
Okay, cool. Then I guess we can wrap up the seminars. And thanks again, Manuel, for the very interesting talk. And like,
yeah, thanks for having me. This was fun.
yeah. See you all like
Cool.
next week. Probably. See you. Thanks.
Goodbye. Bye-bye.